Our next speaker is Bjorn Poonen from MIT, and he will talk about integral points on curves via Baker's method.
Okay, thank you very much, and thank you to the organizers for inviting me here. So when I first was invited, I tried to think, let's see, what of my research is related to Emmy Noether's work, and of course the answer is pretty much everything. It underlies pretty much everything. So I guess I could speak about whatever I wanted. So all right. Anyway, so I'm choosing to speak about some work that I just did in the last, well, the final part of it was just done in the last month or so. This is joint work with Aaron Landesman, who's also at MIT, right? And I'd like to thank also Umberto Zania and other people. So the paper I'm going to speak about was just posted on the archive, so you can see everything there if I forget to say stuff. Okay, so the question is about finding integer solutions to polynomial equations. And so in particular, I'm asking, is there, this is not my question, but is there an algorithm to determine the integer solutions to every two-variable polynomial equation? And well, why two variables? Well, I mean, one variables we know how to do, the rational root test, and they're faster. They're faster methods that don't require factoring integers as well. And if you go up to 11 variables, then it's undecidable to even figure out whether there exists a solution. And so, well, two variables is the first case we don't know how to do. And yeah, so that's what I'll focus on. And if you want to express this problem in more geometric terms, you can ask for integer points on an affine curve. All right, and you can assume it's smooth by just normalizing. Okay, so but before getting to the new results, let me review some Siegel's theorem, which is the main qualitative result about this problem. And before I state the theorem, I'll need the notion of Euler characteristic, which so let me just review some basic stuff. So if you have if you're over the complex numbers and you have a smooth affine curve, so let's call it U, then you can write it as a smooth projective curve minus some finite set. So here, so this is going to be a smooth affine curve, and this is going to be a smooth projective curve, and R is just some finite non-empty set of closed points. So finite non-empty. Okay, and then, well, if in terms of that, then you can express the Euler characteristic, as I'm sure you all know. So in terms of the Euler characteristic of x, and then subtract 1 for each puncture. All right, but the statement of Siegel's theorem is not about curves over the complex numbers. So let me set up the actual notation for Siegel's theorem. So here K will be a number field, so a finite extension of Q, and S will be some finite set of places, of K, and containing all of the Archimedean places. And okay, so in terms of that, you can define O, the ring of S integers, and this is just the set of elements of the number field that are integral, meaning the valuation is non-negative at all the places outside S. So for all so for example, if K is Q and S is just the infinite place, then this condition is saying that you're looking at rational numbers such that no primes appear in the denominator. So those are just integers. All right, so this is going to be a slightly more general version of the questions there. All right, and now we have a curve U, and so U will be a smooth affine curve. And this is going to be, yeah, and all my curves, maybe I should say this too. I mean, all these curves are going to be geometrically integral. I won't, I'll just include that in my notion of curve from now on. And yeah, and this is over K. But in order to talk about integral points, I also want to have a model. So that's this fancy U. So this is any finite type O model of the curve U. Okay, and now I can state Siegel's theorem. So Siegel proved in 1929 that if the Euler characteristic of the curve, well, I guess you can base change the complex numbers and then define Euler characteristic in the way as there. So if the Euler characteristic is negative, then the set of integral points on this model, the set of S integral points is finite. All right, so, okay, good. All right, so before I continue, let me give an example of this. All right, so let's take one of the simplest examples. Is where we take the curve. Okay, we'll let this model be the curve given by the equation x plus y equal 1. But I take this inside GM cross GM. So okay, so the picture is this: I take the affine plane, I remove the axes, and then I take the curve given by the equation, and then so that will be something like this. So x plus y equals 1, but the axes are removed so that this curve has those 2 points missing. And so if you project this onto the first coordinate, then you see this is the same as P1 minus the minus 3 points, 0, 1, and infinity. And I want to think about this as a scheme over the ring O. All right. So if you take, well, for that curve, you can easily calculate the Euler characteristic. So that's going to be the Euler characteristic P1 minus 3 points, which is negative. So Siegel says that the set of integral points U of O is finite. And what is this set of integral points concretely? It's the set of pairs of S units, so units of the ring O, such that x plus y equals 1. So this is called the S unit equation, and so yeah, it'll have finally many solutions. Okay, so as an example of this, or corollary, we could take, for example, O to be the ring where you would join to the integers 1/2 and 1/3, and then it will imply things such as that if you take this Diophantine equation, then this has only finally many solutions. Actually, this is maybe not such a great example because you could do this one by elementary means as well. But anyway, just to give you yeah. Okay, yeah. So all right, but the problem with all this is that Siegel's proof of the theorem. It really only gives you fineness. It doesn't give you the list of integral points. It's ineffective in that sense, and it's ineffective even in theory. It's not just that it's complicated to figure out. There's no way to extract from the proof a list or a bound on the solutions. I mean, I guess if you work hard, maybe you can get a bound on the number of solutions, but you can't figure out how large they are. So okay, so the problem is that this is ineffective. Okay, so that's not the end of the story. By the way, I guess I also didn't talk about the case where the Euler characteristic is greater than or equal to 0, but those are all, there are only a few such geometric types of those, and in those cases we know how to describe the integral points. So I'm not going to talk about those cases. All right, so what do you do if in this situation now? Well, I mean, it's still not known how to make this, how to solve this problem in an effective way, but there was progress. So this is what I want to talk about next. So this is Baker's theorem. All right, so let's see. Have they got? Oh. Okay, this is going to take a little bit of notation to set up. So let me. Oops. Okay, so Baker's method is a theorem in transcendental number theory. This is also called the theorem on linear forms and logarithms. It's about linear forms where you take algebraic number times log of an algebraic number plus algebraic number times another log of an algebraic number, and it gives you bounds on how small that can be in terms of the size of the coefficients and so on. So all right, so here's the statement. So Baker, okay, plus epsilon. I'll explain that in a second. So what did he prove? So okay, so here's the data. You start with a number field, okay? You start and you have an absolute value on K. Absolute value. So it could be one of the complex absolute values, or it could be a p-adic absolute value. Yeah. And actually, it's the p-adic. I mean, Baker did the Archimedean case. It's the p-adic case that's the epsilon. Yeah, and then you have a bunch of algebraic numbers, non-zero algebraic numbers in the number field, and finally you have a positive real number epsilon. Okay, so given all that, so if you fix all that data, then you can ask about the set of tuples of integers such that if you look at the power product, the powers of these algebraic numbers in the number field, and you ask how close can that be to 1, because this is essentially saying this asking how close that can be to 1 is like saying how close b1 log alpha 1 plus ... bn log alpha n can be to 0. So we want to give about, and we don't want to consider cases when this is actually equal to 1. So the statement is that if that there are only finally many solutions where this is very small. And how small is it? It's going to be e to the minus epsilon times the max of the bi. So, I mean, of course, you can make this small enough if you were allowed to choose integers larger and larger. But yeah, so do you want to so it's saying that this cannot be exponentially small very often. So yeah, so the statement is that this set of solutions to this is finite. And in a finite and in an effective way. So it can be effectively bounded. So there's some formula that gives you an upper bound in terms of all the input data. And so, okay, so that's the statement. So, and now how does this get used?
More in a better way than just searching up to that bound?
So if you're given, you mean if you're given particular alphas. I mean, I don't know. I guess you could probably try to do things like I mean, there are probably things you could do with lattice reduction, I would imagine, to find these solutions. And actually, in the applications, there are other tricks you can do if you're trying to find this to solve the S-unit equation. For example, you can combine this. This will give you a bounds on the exponents of the primes, like in the 3 to the R to the S. It'll give you bounds, a big bound on that. But you can do other things like use congruence conditions to rule out many residue classes of R, comma S. And that way, even if your original bound in R and S is very large, you can often solve these problems using those. So it's actually quite practical in for a lot of applications. And yeah, so okay, so let me just give one example of how you could use this theorem. So suppose you're trying to solve that, let me just apply it to trying to find the solutions to this middle board here, this 3 to the R minus 2 to the S. I mean, whenever you have a solution to that equation, you could divide by 2 to the S, and then you would get that 3 to the R, 2 to the minus S is very close to 1. And more precisely, you could ask, yeah, you could take this thing and ask for how often does it happen that this thing is, well, positive, but less than or equal to 2 to the minus S. Yeah, so anytime you have a solution to that equation in the middle board there, it'll also satisfy this. But the Baker's theorem is telling you that this can never, well, only finally often this can be this small. And so it's telling you that, yeah, that this has only finally many solutions. Okay, so that's just one example, but actually you can apply the same idea. So this is what Baker did to study the S-unit equation. So that one on the upper board, because the S integers, they form a finely generated Bilu group. It's not just powers of one number like 3 to the R, but it's a finely generated multiplicative group. And so you can by doing a similar argument, you can use this to bound the solutions to such an equation. All right, so that's how you can use Baker's theorem to say something about Diophantine equations, in particular S integral points on curves. And so then the question is, well, how general can you make this application? To which curves will this let you effectively determine the O integral points? And this is what's not yet known. Yeah, so this is what the rest of the talk is going to be about. All right, so let's see. All right, so just let me just repeat what I was just saying. So this is just one application, but you can also, so Baker's corollary, which he did it around the same time, and this is that this set of integral points is a computable, it's a finite and computable set for certain curves, for certain affine curves. And such as the one, yeah, such as the S-unit equations. Okay. Now, okay, so this is where things stood in the late 60s. And later, Yuri Bilu found a way to use Baker's theorem in a more general way. So this is to have it apply to more affine curves. So I want to explain what he did. So, okay, so I want to introduce a term to describe the curves to which this generalization will apply. So let's call a curve. So this is the curve over a number field. Let's call it, or it could be even over any complex numbers or whatever. Let's call it good. And maybe that's not a very creative name for curves, but yeah, but I mean, I was thinking I could call it beautiful curve, but no, but I think I'll stick with good. Yeah. All right, so let's see. Oh, by the way, the epsilon in the Baker plus epsilon it's not the same as the epsilon greater than 0 there. If you look closely, you'll see that one of them is a var epsilon. So, okay, anyway, here's the definition of good. So it's good if there exists a non-degenerate map. So, okay, so here it's generalizing this example here, but it doesn't have to be x plus 1, y equals 1 in GM cross GM. It could be essentially any curve in GM cross GM. And it doesn't even have to be in GM cross GM. It could be a curve that maps to GM cross GM. And you just need some kind of non-degeneracy hypothesis. And so, okay, so there should be a non-degenerate morphism. So to GM cross GM. So to GM cross GM. And okay, so what does non-degenerate mean? Maybe I can squeeze this over here. So non-degenerate means if the image is not contained in a subgroup or a coset of a subgroup, in a coset of a proper subgroup, proper algebraic subgroup. Okay, so yeah, so essentially saying that U has two independent maps. It has two independent morphisms to GM. So all right. And so okay, so that's just a definition. So what did Bilu prove about these? Well, you can probably guess what the theorem is. It's just that the theorem is simply that if you have such a curve, is that if U is good, then the set of integral points on any model is computable. It's fine. I mean, it's already finite by Siegel's theorem, but now it's computable. And so that's and the proof is the proof of this is not very long. It's like 2 pages or so. And again, just once you have Baker's theorem. And as for the proof, I guess I skipped the proof of Baker's theorem. So the proof, well, maybe all I can say about that is okay, but all right. So, so now the question is, which curves are good? So what does it mean for a curve to be good? It means that if you take each morphism from U to GM, that's the same as giving an invertible function on U. And to say that you have two independent ones that are non-degenerate in this sense is the same as saying that if you consider then the rank of the group, if you want 2 of them, and so modulo constants, the rank of this group should be the Z rank of the abelian group. That should be at least 2. And so you could also say this in terms of having, if you take the divisors of those functions, then that means you should have 2 independent principal divisors. On the projective curve that are supported on the punctures, so that they're regular and non-vanishing on U itself. So they should be supported on the finite set of punctures. And that you can also restate. To say that a given combination of points in R is principal, that's the same if they add up to 0 in the Picard group. So you can also rephrase as saying that you want 2 independent relations between the points of R. Well, okay, maybe between point. since I'm running out of space, let me just say I'll just say two independent relations in R, well, in the Picard group of the projective curve. Okay, so I mean two combinations of elements of R that should either give you 0 in the Picard group. Okay, so it's actually, so given any curve, you can test this criterion, and you can figure out whether it's possible to use this Bilu's enhancement of Baker's method to find the integral points. And so the question is, yeah, does this always work? And well, I mean, if this does not work, if this condition fails, which it will, for example, if there's only one puncture, because if there's only one puncture, there's no way you're going to have any relations. So then what can you do? So you can, well, there are ways you can try to reduce the problem by changing the curve, or by changing the number field and the set of an S. So, okay, so there are a couple of things you can do. So one is, yeah, so if these conditions fail, so then as Bilu noted, you can try these various things. You can, for example, you can, well, this one by itself won't usually help much, but you can enlarge the number field, or you can enlarge I'm not just making things harder, but more useful is you can combine this theorem with the method of descent. So maybe in the form, maybe I'll attribute it to Chevalier and Vey descent. So this is a generalization of Fermat's method of infinite descent. And so what you do here is you replace the original curve by a finite etale cover. Finite etale cover. So U prime. Yeah, and the point is that whenever you have such a finite etale cover, then, well, you can extend it to a finite etale cover of the models, and then any O integral point on U, well, it might not lift to an O point on U prime, but it will lift to some point in a finite etale cover of O, and that'll be an S integral point for a slightly larger number field. And so one has that the integral points on U are contained in, let me give let's give this cover a name. Let's call it F mapping U prime to U, and then I want to say that all these integral points downstairs on U are in the image of the, well, some O prime points on U prime. So this is for some computable, some a priori computable ring of S prime integers and some number field K prime. So one with, yeah. Okay, so by this that means you can, if you don't like your curve U that you started with, you can replace it by this finite etale cover, and maybe it'll become good then, even if your original curve was bad. And so maybe you have some hope of applying Bilu's theorem to that U prime. And then if that's true, that means that you can find this finite set of points, and you can compute its images, and then just check each one individually to see if they're actually O points on U. And so you'll have an algorithm then for use. And yeah, this actually, I mean, there are some nice examples of this. So in fact, this method was, I mean, this was used well before Bilu's theorem, because you could also comply this with the original Baker's examples. So yeah, so let me give one example of this. Okay, so let's do this example of, which is due to Baker and Coates. Um, 1970. Okay, so Okay, so this is going to be an elliptic curve. So we're going to talk about integral points on an elliptic curve, by which we really mean elliptic curves on integral points on an affine elliptic curve, which means we're going to puncture it at the point in infinity. So, okay, so here E is a projective elliptic curve. We remove one point to get an affine curve U. And okay, so now that curve is bad because there's only one puncture. There are not enough relations between the punctures. So then we'll replace U by the étale finite étale cover given by multiplication by 2. Okay, so U is E minus the origin. Yeah, so this is bad. But if you look at multiplication by 2, then you get, well, you get a U prime that's, yeah, so if you pull back this under multiplication by 2, then you get E minus, and then instead of just one point removed, now you remove all the two torsion points. So now you have E punctured at 4 points, and well, and the 4 points you remove, well, there's some, this is going to be good because, well, these 4 points have some obvious relations, like 2 times any one of those points is linearly equivalent to 2 times any other point. So that gives you, yeah, and so that gives you enough independent relations to pick for you to apply the theorem. So this is how Baker and Coates gave an algorithm to compute the integral points on any elliptic curve. So by passing to this cover and applying the method there. Okay, and in fact, this works. I mean, this actually handles all cases where the genus of your curve X is less than or equal to 1. Because I mean, the other cases, well, if you have more punctures, that just makes the problem easier. And if you have P1, well, then it has at least 3 punctures, and it's basically the S unit equation. So yeah, so the conclusion of all this is, so thus, for all the cases of genus less than or equal to 1, that's all done. And so all that's left to do is handle all the rest of the genus, all of G. Okay, so all right, so now the question is, can you do how effective is this method? Can you do this, for example, can you do this for all genus 2 curves? So it turns out, for example, there's a similar thing you can do if you have any hyperelliptic curve punctured at one Weierstrass point. And then there you can do a similar method. And yeah, you can read about this, for example, it's well in Serre's book Lectures on the Moore-Delvey theorem. And so but the question is, can you how general is this? All right, so yeah, so the big question now that's implicit in Bilu's theorem is every curve susceptible to this message? So does every smooth affine curve over any number field? So it's over any number field, okay, of genus at least 2. So does it admit a finite étale cover that is good? Okay, so this is the big question that I want to talk about for the rest of the talk. And the stakes are high, because if the answer is yes, that means we have an algorithm to solve all 2 variable, find integer solutions to any 2 variable polynomial equation. So yeah, so the question is could there be some clever geometric construction? You just use the right kind of cover, and these could be non-abelian covers too. So there are a lot of covers you could try. All right, so yeah, so that's. Okay, yeah, you need to, but I guess you could just search. You could just try them all. I mean, you can enumerate all the covers. So yeah, so maybe you don't like that kind of algorithm, but it would be something that terminated. Even if you just know it exists, you can just try all covers until you, if you have a theorem that guarantees that it exists, you can just keep searching until you find it. Okay. All right, so okay, so the let's see. So okay, so we conjecture the answer is no. So we don't think it's going to work. And as evidence for this, so here's what we can actually prove. If you take that question, but you replace q bar by the complex numbers, then the answer is no. So this means that there's not going to be sort of a generic construction, say, that works for all genus 2 curves. There's not going to be like a particular construction of a degree 72 cover that sort of universally works for all genus 2 curves, because then it would work over the complex numbers as well. And so that means that if this answer is going to be yes, it's going to have to be something crazy like in Bilu's theorem or something, where you have your cover, the degree of the cover depends on the size of the coefficients. And I don't believe that. Well, I don't believe that's going to happen in this case. So that's why we conjecture no. But yeah, we don't know for sure. Okay, and in fact, we've proven no in a stronger sense. So let me state the stronger version of this. So that it fails for there's a failure for any smooth projective x of genus at least 2 over the complex numbers. Any of genus greater than equal to 2 over the complex numbers. There is some place you can puncture it. There's some point such that, yeah, so if you puncture this in a bad place, then the resulting smooth affine curve has, well, not only does it not have a cover with 2 independent maps to GM, if you puncture in the wrong place, you can't even find 1 independent map for any étale cover. So this affine curve has no finite étale cover. No finite étale cover with even one. With even one non-constant morphism GM. Okay, so I can restate that in terms of by going through these translations here. I can restate that in terms of independence of points of independence of points in the Jacobian of the cover.
Then would make a higher chance of getting more.
Okay, yeah, you could, yeah, so you could ask, yeah, you could ask for, you could try to remove more than 1 point, and maybe, yeah, maybe you would have a chance. It might be that if you're, yeah, it's conceivable that if for every curve, if you remove, well, not every curve, but if you remove for example, it could be true that for every genus 2 curve, if you puncture it at 2 places, maybe there could be a cover where you have enough relations. But if you really want to have an algorithm that gives you integral points on every curve, then it won't be enough just to consider those, because there's some polynomial equations that will be equivalent to the problem for having just a genus 2 curve with 1 puncture. And so, yeah, so I mean, so this is really just saying that there's not a general method that's going to work. I mean, if we could prove this theorem over Q bar instead of C, then that would prove that Baker's method with Bilu's method with finite etale covers are not enough to give you an algorithm for all two variable polynomial equations. Okay.
But you mean integer point is not what ordinary people mean by integer point.
You mean because I'm using S integers, you mean?
No, I mean like for x plus y equals 1, yeah? I mean, you know, we know many integer solutions of that.
Oh, okay, but yeah, so
The point is.
yeah, that's true. On the other hand, for any of these equations, you can re-embed it into an affine space such that the integral points are really just the integral solutions. So in some sense, it really is. I mean, this really is related to the problem of just it's essentially the same problem of asking for integer solutions to just f of x y equals 0 in the naive sense. Okay, all right. So yeah, so before I talk about the proof of this, let me just restate this condition here. When I say this curve has no finite etale cover with even one map. So this condition here, I can restate in the following terms. I can say it's saying that for every finite etale cover of this punctured, every finite etale cover, or sorry, I'll talk about the projective curve. So let's talk about curves that are any finite cover y to x, but ramified only at most above the point above that one puncture, ramified at most over the one point x. The preimages the preimage of the puncture in this cover of x are independent in the Picard group. So they're z independent. In the Picard group of y. Okay, so that's another way of saying what the theorem is. All right. All right, so let me now try to explain some of the key ideas of the proof of this. Okay, the first thing I want to say is that although this statement is a statement about all finite etale covers, it's enough to talk about the Galois etale covers, or Galois covers that are ramified at most over x. And that's just because every finite etale cover is dominated by some Galois etale cover, and if you have a map to GM after some finite etale cover, you'll also have that map coming on any higher cover because you could just go through the first cover. So yeah, so all right, so let's see. So final. This is going to be the proof of the stronger theorem. Okay, so what I was just saying is that it suffices to consider Galois covers consider Galois covers. Covers. So okay, so y to x. So possibly ramified over the puncture, possibly ramified over the point little x. All right, and so, well, I mean, so let's try to check this condition one group at a time. We'll just do it for each Galois group. So for each finite group G, well, then if you fix the curve x and you fix the puncture and you fix the group G, then there are only finally many covers. There are only finally many G covers that are ramified outside X. This is, I mean, you can understand this analytically because these correspond to maps from the fundamental group of X minus the point to surjections from that onto G. And there are only finally many of those because the fundamental group is finally generated and G is finite. So yeah, so then you can all those will be algebraic then by the Riemann existence theorem. And so you can describe them. And for simplicity in this talk, let's just pretend that instead of having finally many, let's just pretend that there's just one. I mean, that's not true, but it's not going to affect the proof much. So assume there's just one G cover for each position of the puncture. So okay, so and let's also assume that we're able to label in some coherent way the preimages of that point in Y. So let's call them, and assume that y1 through yn are the distinct preimages, are the distinct preimages of X. So the preimages. Yeah. All right. Distinct preimages of this possibly ramified point of X. Okay. So yeah. So let me draw a picture of this. So. Okay, so I have a curve. All right, so here's a curve. This is the y, and it maps to some curve over here. This is the x, and so there's some cover. And here there's a puncture x, and the preimages. Well, okay, I can't draw them all in the line. I mean, they should be all lined up with x, but let me just draw them here. y1, y2, yn. Okay, so y1 yn. Those are the points that map to x. And I want to consider. I'm trying to find this puncture such that all these points are independent in the Picard group of y. And so, so I need to be able to move this point x and see what happens. And this cover, well, which I've simplified by assuming it's unique, but it does depend on x. So it's really a curve that depends on the puncture. And as you vary x, you can show by an extension, by version of the Riemann existence theorem, that this varies in a smooth family. And so you get, yeah, so you get a surface. So maybe I'll call it a curly y that consists that's fibered over the base x, which is recording the position of the puncture. And so, I mean, x is playing this sort of dual role. It's on one hand, it's parametrizing the curves, and on the other hand, each of those curves is a fine cover of x. And so this is sometimes it's called a Kodaira-Parshin family. Okay, anyway, so you have this, and so and here's the So this is the curve parameterized by x. And so, I mean, one thing we try to do is try to say, so, okay, suppose you start with a point for which these are related. There is a relation. Maybe you can show there's a first order deformation of this, such that the relation breaks as you move the curve away. Because these points, these preimages are also going to move in a smooth family. And so actually they're going to be you're going to get they're going to give you some divisors on this surface. And so let's call those d1 through dn. And I mean, and the combinatorics of these things is all the same by the analytic description. So these are actually disjoint divisors. I mean, I guess in general there might be some monodromy. They might hook up and make one curve, but by passing to an additional finite cover, I mean, instead of working over x, I could pass to the finite etale cover of x to get a different moduli space, some sort of Hurwitz scheme, so that not only I have the individual curves. I mean, yeah. So there, if I didn't have just one, I would want to pass to a cover where I actually parameterize one point, not just for the recording the x, but recording which curve above, and also extend it further to have these be disjoint. Okay, so let's suppose I've done all that. And so now, yeah, so this is really some Hurwitz scheme that's a finite etale cover of x. But anyway, so you have that. And well, down here, and we want to show that there's some position of this x such that the preimage points are independent in the Picard group of that fiber. And so how do you do that? Well, it's actually equivalent to ask the question for the generic point. So let's say this is the generic point of x, and look at the points in the preimage there. And so, yeah, all right. So let me now write what I want to. Let's see. It's running out of the good chalk. All right. Well. All right. So here we go. Okay. So, all right. So to prove the stronger theorem, it would follow from the following claim that for all but countably many points, of the complex points, these preimages are independent or Z independent in the Picard group of the cover, which is Y sub x. And well, I mean, if you have that certainly implies a stronger theorem, because they're uncountably many points here, and there are only finally many points that will give you a relation. So that means if you choose any point that's outside that countable set, you'll have these points being independent, and then you'll have this condition. Yeah. So okay. So and to say that this holds for all but finally many points, then that's the same as saying that it holds for the generic point. So let me write that. So yeah, by the way, we're never able to make the deformation theory argument work. Maybe it's just we don't know enough about how to deform curves and morphisms between them, but maybe it works. I don't know. But anyway, so we eventually did this other argument, which I'm in the middle of describing. So yeah, so we want to prove this claim, and that claim is implied by another claim. So let's call it claim prime. As I said, you just have to check this for the generic point. For the generic point, eta, then the same thing. The preimage are independent in the in the Picard group of that generic fiber. But now the advantage of this is that now you can rephrase this in terms of the classes of these divisors D in the narrow Severi group of the surface. And so this is the same as saying, so claim double prime. So this is the same as saying that if you take these n divisors that are recording the preimages, well, I mean, if to say that their generic fibers are dependent in the Picard group means that if you close them up to get the divisors, it doesn't quite say that they're independent, because it could be that it just means that there's a combination of them that's only vertical. So if you're and this is a smooth proper morphism going this way. I mean, because all the fibers are these, it's a smooth proper family everywhere, good reduction family of curves. So all the fibers are equivalent in the narrow Severi group. They're just one big algebraic family. And so to say this, it would be enough to say that if you take any one fiber, let's call it y sub 0. So I'm just choosing one particular fiber up here. So let's say, okay, so I have just one point here, 0, and the fiber y0, just a class of a fiber. That's all I need. And so it's enough to say that those are independent, are Z independent in the narrow Severi group of this smooth surface. And so, okay, how can you check that? Well, you can do the usual thing by trying to compute the intersection numbers of these divisors. And so this is what we did. So we calculated the intersection matrix. So we're doing these intersections on this y, which is this universal curve over some Hurwitz scheme. And it turns out that this intersection matrix, well, okay, what is it going to be? So, well, first of all, the D's are disjoint. So they're going to be zeros off the diagonal for that part. Oh, and the fiber is intersects any other fiber in 0. So there's a 0 here. There's some numbers along the diagonal, but then, oh, and each of these D's intersects the fiber in 1. So there's going to be ones along here. There's going to be ones along here. There's some number, which is, we don't know what it is yet, but it's going to be the same for all the D's because the Galois group permutes them. And then, yeah, so there's a diagonal matrix here, and all zeros up here, all zeros here. And so it's a matrix that looks like that. And well, if you're good with determinants, you can figure out what the determinant of this is. And it's up to a constant, it's a power of D. And so where D is the self-intersection of each of these divisors. And it turns out, well, if you compute that number, fortunately, it turns out to be non-zero, at least when G is greater than 1. So it turns out to be a multiple of 2 minus 2G. It turns out to be negative, in fact. So this, okay, so I'm continuing so for some D, that's negative. So good. So this matrix has non-zero determinant. And so that finishes the proof. So you know this, so you know this, blah blah blah. All right, so that's it. I'm basically out of time, but in the last 30 seconds, maybe I could just say, okay, what would you need to do if you really want to prove this stronger theorem over Q bar? Because this is saying there's some countable, and this argument shows there's going to be some countable set of points where there could be a relation between the preimages. And we want to know that countable, I mean, the problem, of course, is that X of Q bar is also countable. So this set of exceptional X's could actually be all of it. Now, what we can say, so I thank Umberto Zani for suggesting, yeah, observing that if you can use, if you fix one group G and you ask for, and you look at this family and you ask what are the X's for which those fibers are independent, you can use Silverman's specialization theorem to show that that happens only for a set of bounded height. So these exceptional x's for that one group G are a set of bounded height. And now the question is, what happens when you take the union over all possible G cover, all possible groups G? So if you had some uniform version of Silverman's theorem of bound height, if you had that, if that bound on the height was uniform in G, then you could take the union, you could then any point of large enough height would be non-exceptional, and you'd have the theorem over Q bar. But I've never seen any result of that type, like sort of uniform. It's kind of a complicated uniform thing because you have to look at all the finite etale covers. But yeah, so that's where things stand. So yeah, so thank you all for your attention. So. First, also, well, I guess it's traditional for the last speaker to thank the organizers, and so, and I think this time, I mean, I think the organizers really do deserve thanks for having this great lineup of speakers, and I'm sure they did a lot of work putting this together, and also all of you. So thank you very much.
I have one, since you mentioned Zania, is there some conjecture in unlikely intersections that might imply this?
Well, yeah, I don't know. I've never seen one that applies to this kind of thing to all. I mean, it's all étale covers of a curve. I mean, I don't know very many statements of that. I mean, other than belly down, there are this kind of.
How are these silver pink type things? Like, Zania would have noticed if it did apply.
Yeah, well, he's okay. Yeah, so I guess he didn't know.
But it would be another conjecture anyway. But I guess it's
yeah. I don't know if there's any. I don't know if there's any.
Since you're proving something negative, then it is relevant one conjecture.
Yeah.
And it's good to
understand
the connections between.
That's a good question. I just don't know if. I guess Umberto doesn't know. I guess I don't think there is such. At least there's not. I don't know of any obvious relationship between this and other conjectures.
Before there's another question, guys, please don't leave. Jay would like to make an announcement at the end of the question. Okay. All right, more questions.
What about like higher dimension analogs? So for instance, let's assume that we have maybe no confinedness, some statement about like density of points. Can we do again like a same definition of good, but in the product like a GM to the dimension of the, let's say that just we are looking at the hypersurface, so the dimension of the hypersurface. That's one.
Okay. Yeah.
Okay. Are we using like, so like maybe like my question is in the end, are we using that solutions are divisors, or can we just like replace like in a stronger theorem X with a divisor to find over C and do the same?
Okay, yeah, those are good questions. I don't know how much about if there are extensions of Baker's or ways to apply Baker's theory to study, to say things about integer points on higher dimensional varieties. I mean, there are analogs of Siegel's theorem based on things like using, for example, Schmidt subspace theorem and things like this that will tell you some qualitative results. But as far as making them effective, I don't know. Maybe some other people know more about this, but I think it'd be hard. I think it's hard to get started with that. There probably are, but maybe if you assume enough conjectures, maybe you can say something. Yeah.
Other question? I have one. So if the goal is to count these integer points, can you replace the affine curve with another affine curve with the same projective completion, and then maybe you can write an algorithm for that?
So if you replace the affine curve with another affine curve with the same projective, in other words, you have punctures in different positions.
Yeah.
The location of the punctures completely changes the problem as far as I can tell. So I don't know. Usually there doesn't seem to be any easy way to go between the curve that punctured at one point and the curve. So for example, in the genus 2 case, as I was mentioning, if you puncture a GS2 curve case at a Weierstrass point, then Baker, you can use this combination of Baker's method and étale covers to find all the integral points. And you can even do this in practice. So, but if the puncture is somewhere off that, then it's an unsolved problem to find the integral points if you puncture on the wrong place. And this is suggesting that it's going to be pretty tricky to use these methods, probably, unless there's some things where it works over Q bar and not C. It's going to be pretty tricky to do this.
Other question? Oh, right.
So we just wanted to say thank you to a lot of people quickly. So thank you to a lot of the Institute staff that made this be possible, especially Michelle. And then thank you to all the speakers for giving great talks and coming here and showing us how influential Noetherian ideas have been throughout the last 100 years. So thank you all.